whatever the word I'm looking for. Right, so I have that guy, which I believe looks like a bit like a hat. And I got this guy. And it's the volume between these two, essentially, is what we're trying to get. It's kind of hard for me to work with this, so I'm going to put my phone down and hopefully you can still hear me. So let's get started. These two guys, well, our triple integral is going to be 1 with respect to dv, right? We're going to be doing a theta. We're going to be doing an r. And we're going to be doing a z. Now, these two guys are going to represent eventually anyway, these are going to represent the z's. This one, for instance, just turns into z equals r squared. If I rearrange this one, you get z squared equals 2 take away x squared, take away y squared, which is that guy. And z then is going to be that fella. And I'm assuming that we're talking about the positive one. So far, so good. Now, where do these two darn things intersect? Well, if I call this equation 1 and I call this equation 2, and I convert the z's into r's, the first guy looks like that. And this gets you r squared plus z squared equals 2. If you square this guy, z squared is r to the 4, which means I can replace this guy with that, and now I have r squared plus r to the 4 equals 2. And if I solve for this, I should be able to figure out what the r values look like. Right, well, if I rearrange this fella, I get that. Do you recognize that as actually a quadratic in r squared? I know it's unusual, but it can be done. And so I have an r squared, I got it over here, haven't I? I got a plus 2 and a minus 1 equals 0. And that gets me r equals -1 to r equals 1. But we don't have that guy, so we got a 1. So that was a lot of hard work just to find out it was 1. So r is going to go from 0 to 1. Theta is going to go 0 to 2 pi, very obviously a circle. And z is going to go from that guy to this guy. And it's going to be this way around. That guy is z equals r squared. This guy is that. And why did I pick it that way? Well, I've got an answer in front of me here, but if I got it wrong, the volume would be negative anyway, so it would be too difficult to figure out what it was. I could do by numbers. If I plug in a number like somewhere between 0 and 1, right? This is a numerical way of deciding. Pick a number between where there and there is. If I choose a half, this is a quarter. And if I choose a half, this guy is a square root of 1 3/4, which makes this guy bigger. So this guy does go on the top. And the dv should have came out as dz r dr d theta. So I've got this fella, got this fella, this fella. If you take 1, you get z, so basically you're going to get zr dr d theta. It's going to be 0 to 2 pi. It's going to be 0 to 1. Okay, you plug it in once, you plug it in twice, what do you get? One of them ends up looking like that. Take away that guy. Okay. would you agree that I can integrate this fella and just use a power rule? What will I do to integrate this mess?
U sub.
Yeah, and the U sub will be 2 take away R squared. Can I just dot this, because it'll take forever and a day to finish it? But we know essentially what we need to do to get the result. So far, so good?
I have a question.
Yes.
On the left page, why did we take r equals 1 when, like, could we also have taken square root of 2?
Oh, not really, because that would be the square root of negative 2, which is a complex number, which wouldn't be a good idea.
Oh, okay. Okay, thank you.
Be done. It's a good question. I bet you other people were thinking about it. Can we call that one done? I mean, I could keep going, but it's really just messy, isn't it? It's Calc 2 stuff. And isn't that guy there just going to get you 2 pi because it doesn't even have a theta? So that's the end of that one. Where are we going here? Oh, this is a question 11. You got, or at least a version of it, negative 66. Negative the square root of 36 take away y squared, and a positive 36 take away y squared. And then another integral of the square root of x squared plus y squared, and a 9, and then x, z, dz, dx, dy. Okay, what we're looking at here is a very messy expression. If I try to do this integral the way it's set up here, I would definitely end up with a lot of issues. I'd end up with integrations that are very difficult, maybe even impossible. So question 11 and question 12 says, redo this guy, but do it in polar. Technically cylindrical, but you know, essentially convert these to polar. Now I'm going to have to put some variable names in there. That guy there is y equals to y equals. This guy is x equals to x equals. And this guy here is z equals to z equals. Now let's see if I can make some sense of these guys. If I tell you x is this fella, if you square both sides, you get that. And if you rearrange both sides, basically, don't you get that? What that is telling me is that we're looking at a circle. And the circle is radius 6. Agreed? Now, if you want to do a radius of 6, won't you just do theta equals 0 to 2 pi, r equals 0 to 6? Now, what about the z? Well, one of the z's is quite nice. And if you convert z equals this guy, doesn't that just become z equals r?
Yeah.
Now, I've got an xy to deal with. Well, we know what x is, isn't an x in r cos theta? Times a z times an r dr d theta. Are you happy about the xz becoming this mess? dr theta. Is there in and about what I have just done here that doesn't kind of, you're not sure where it came from?
Don't you need a DZ?
Say again?
Don't you need a DZ?
Oh yes, yes, I do. Apart from the fact I left that out, we good? Right, let's take it a little bit further then. So I'm just going to focus on right now doing this piece. So that's a Z. So that's going to get me 1/2 R cos theta Z squared, evaluated at Z equals R to Z equals 9. And then the other two integrals will come later, right? So that's going to be 1/2 R cos theta times 81. Take away 1/2 R cubed cosine theta, dr d theta. And the R is going to go from 0 to 6. And the theta is going to go from 0 to 2 pi. Are we good so far? Right, now I'm looking at this and, you know, I'm just hoping.
Question.
Yes.
Sorry. Do we have to add the other R in? So it's R squared?
Did I do that? That could be me. Do we need the other R in? And we do. Yes. So that's just me being careless.
Okay.
I'm looking at this darn thing and I'm trying to see if there's anything I can do to make life easy, and I'm going to have a shot at this. I guess after I write this, I'll figure out if it was worthwhile doing or not. I'm going to pull out a cosine theta. Why do you think I'm doing that?
It's just 1/2 R cubed.
Okay. Why am I doing this pulling out cos theta thing? What do you think the reason behind it is?
You can separate variables.
Right. So it's not much of a benefit, but it's better than nothing, right? Can we dot that now? Would you agree it's pretty much finished?
Yeah.
That's okay. I'm going to move this guy. There's one last version of this thing, I think. Should get it set up. Right. Basic same idea as the last one. Obviously some changes. What is -5 and 5? Which variable is associated with this last integral?
X.
X. Would you agree then that Y is this fella and Z is this fella, right? Now, I'm going to take this middle fella, and that's the Y equals the square root of 25 minus X squared, and the Y equals 0. I'll hold on that one. If you square this guy, you get X squared plus Y squared equals 25. You agree? And if you add this fella in and you put those together, well, that's what X squared plus Y squared equals 25 looks like. What does the Y equals 0? How does that alter the fact that it isn't really a whole circle there?
It just makes it a semicircle.
Yeah, in fact, isn't Y equals 0 me? You're talking about the top half. That makes sense? So because we are only going to do the top half, that does alter just a little bit what goes on here. And we're going to go theta equals, we're going to do r equals, oops, a minute. And we'll do the z in a minute as well. If you want to describe this fella, don't you do r equals 0 to 5? To represent the top half, it's not 0 to 2 pi. Do you see it's now only 0 to pi? Now, what about this fella? Well, that fella's easy. Would you agree he's r? If you look at this guy up here, doesn't that eventually become 25 take away r squared? And doesn't this guy just be 0? And then we're going to go dz r dr d theta. So that was a wasted line. I probably said that. Okay, we stick a z in front of this guy. Let's see what we get. Well, you're just going to get an r squared z, so you're going to get an r squared times this guy. Take away nothing. Not really that much to do now.
It's variable separable, right?
Yeah. So basically, wouldn't you just get that answer and do a times 2 pi? So you just separate them up. There we go. I think there's a question I did skip by, but it's a centenary mass question, so they just take forever in a day, but they're only one of them, so I guess it's not too bad. So I'll just leave that one for you. So far, so good. Really glad that you lot are mature enough to help me out here. My brain is, I don't know where it is. Just somewhere else. Okay, let's get to a look at what is next. You should be on spherical. And yeah, okay. Give me a few more seconds. I'm getting a PDF set up here. And I should be able to make this bigger. Okay. So, okay, I've lost you. Where are you? Come back. There you go. Well, the next section, we're just going to do a basic intro to it so you can get a kind of feel for what's really going to happen next week. And it's this fella here. We've done Cartesian, right? dx, dy, dz, right? Triple integrals with x, y, z. And we've done triple integrals with cylindrical coordinates, which are really just polar coordinates with a dz tagged on. There is one last way of describing points and surfaces in 3D space that's not x, y, z or cylindrical. And these are called spherical coordinate systems. So spherical coordinate systems are very useful in a niche market. And the niche market is anything, as you might expect, involving surfaces that are spheres or parts of spheres. As a coordinate system, spherical coordinates would probably be more useful if you're trying to describe where something is in space. I'm talking about in, the galaxies and so on. Now, what you could simply do is, because of being human, you might decide that the sun is the origin. And if you want to tell someone where a particular planet or star system is, couldn't you direct someone to where to look by giving them two numbers, which are the orientations that you would use to point your telescope? And those two numbers would be an angle theta, which is you're on the ground, you face north, and then you turn theta radians. The second angle is called phi, which is you then look up a certain number of degrees. And the last number is called rho, and it says that the thing you're looking at is 2 billion miles that way. Right? It's the distance from the origin. So when you are looking at spherical polar, there are going to be three variables. The first one is theta, the second one is rho, phi, and the last one is rho. Now, I know that you Americans can't say theta well. Let's go for the other two letters. How do you say phi?
E.
E.
You put an E sound in it. You call it phi.
I've heard phi, but I say phi.
Those who say phi, I'm on your side because you're saying it right. Those that saying phi are just weird Americans. Would we all agree that the third letter, this P symbol, it looks like a P anyway. Are you all comfortable that that fella there is called rho?
Yes.
So we all agree on rho.
Mm-hmm.
Nobody apart from me thinks that you say it theta, and some of you call it phi and some of you call it phi. Right, well, I'm too old to change, so you just get used to what I call it. One of the reasons I put this here is, if I tried to draw that, I'm not sure it would be that good. But would you agree even the textbook's not that good? It's very hard to describe a 3D thing on a 2D piece of paper, or in this case, a 2D PDF. So let's show you what some surfaces look like when you describe them in spherical coordinates. Do you know the surface of a sphere is just simply rho equals 2, rho equals 5? The angles don't matter, because you'll use every combination of angle you could think of, right? If you wanted to do a plane that goes through the origin, and it has to go through the origin, its equation is theta equals a number, like theta equals 7, or more likely theta equals pi upon 2, or theta equals pi upon 4, because the number represents the angle in the xy plane. So theta equals 10 says, do every point that goes in that direction, including vertically upwards. The surface of a cone, interesting, and pointing up and pointing down. Now the next fella is kind of like the polar equivalent of conversions. Remember, in polar, x is r cos theta, y is r sine theta, and z is just z. In this case, x is rho sine phi cosine theta, y is going to be rho sine phi sine theta, and Z is rho cosine phi. And there is a nice equivalent relation. Remember in polar, r squared was x squared plus y squared? Yeah, it was quite a useful thing to know. In spherical coordinates, rho squared, which is kind of like the r, rho squared is x squared plus y squared plus z squared. Are we happy about that? Okay. Now, there's a strange extra condition on polar that doesn't seem, well, one of them anyway doesn't seem that obvious why you would need it or even think about it. Let's do the obvious one. The convention is that rho is greater than or equal to 0. So you can't have a rho that's negative. Does that restriction make sense? Can you imagine why rho has to be a positive number? Because it's a physical distance right from the origin. That's why r has to be a positive number as well. Can you remember in a question I kicked out r equals -1? I only used r equals 1. That's the same kind of reason. But why on earth do they only have that restriction? Why is phi 0 to pi? Why do you not need or even should use anything more?
Because there's 180 degrees in between the positive and negative z-axis.
A very clean way of saying it. I know it's hard to imagine, but can you see this angle phi? If it's 0, aren't you up vertical? And that's all the positive z's. And if you use pi, you're going to curve this way, right? I'm assuming you're going to curve this way, right? Won't phi equal pi be the negative z values? So from 0 to pi is all you ever need. Does that make sense? Right. So there's just little restrictions. So if you're ever doing a triple integral, and for some reason you think that this guy here should be 2 pi, or some other number bigger than pi, or negative for that matter, will you rethink it and figure out how you could rewrite it in terms of these constraints? And let's skip by that, actually. Is there any questions about that? Are we cool? Right. I'm going to leave this fella then, and we're going to return now to our camera. And that's basically a summary of everything you need to know, right? I'm not even going to try and draw the picture. You know, I'd make a mess of it, you know, that theta, phi, and rho thing. But we would like to do a triple integral in it, right? So I'm not going to do any of the hard ones today. That'll be for next week. I'm going to do ones that are already set up. So suppose you're asked to do a triple integral, and theta is going to go from 0 to 2 pi, and phi is going to go from 0 to pi, and rho is going to go from 0 to 2, and oh, darn it, in space. I've got to show you something. You can hold off a few seconds. Why don't you take attendance and say hi right now? I don't want to screw this up, so I want to double check that I'm telling you the right thing. Okay, I have what I need. I never can remember this thing. I'm writing it down from here. Got that? Check it. Rho squared. Okay. Now, where the heck are we? See this little guy here? The whole package? That's dv. I wanted to check that I got this bit right. If we looked at dv, remember dx, dy, dz, didn't that turn into an r, dr, d theta, and you can stick the z at the front, right? Do you notice that you got that little weird r left over, or extra? Right. And that was caused by using cylindrical coordinates. Do you see this little extra bit here? That you get when you do spherical coordinates. That's always there, just like the RDR is always there. Right, let's suppose I have a function here and I'll just make it 1. So basically I'm finding the volume of this shape, and I wish I hadn't done that now. So it's going to be from 0 to 2 pi, from 0 to pi, and from 0, I won't need 0 to 2. I will integrate this with respect to rho. So that will be 1/3. Oh, I knew my day was going to be like this. I'm going to change what I did. Nothing major, but nonetheless important. Do you notice that this is variable separable? And my brain just wasn't focusing well enough. There isn't any thetas, at least, because that was a 1. So won't the theta just be 0 to 2 pi of a 1? The phi uses this guy, so that's going to be phi equals 0 to pi of a sine, which I can live with, and d phi. And then we have the 0 to 2 of the rho squared, d rho. Now, I could have, if I thought, but I'm not changing it now, but couldn't I have told you that that one was r squared sine phi cos theta, right? I could have gave you some other bits. If I had done that, wouldn't this still be variable separable, but it would just have more pieces to it? This guy we can do, and he's basically 2 pi. And this guy, well, he becomes a negative cosine. And this guy becomes 1/3 r cubed. Plug in pi. The pi is -1, so -1 is 1. That's weird. Pi, cosine pi is -1. That's 1. Take away 0. Ooh. Okay. Just want to give you an answer that's not 0. So I can pretend that was theta over 2. Right, that's better. Because what do I get out of that? Well, I got 2 pi out of this. I get a 0 take away 1. I get a -1 out of that. And I get 8/3 out of that. So this particular triple integral is that. So it's definitely not a volume, right? Whatever it is. Okay, that one I made too many changes. So I will try a different one for the next and final one. Let's do 0 to pi upon 4. Let's do rho 0 to 1. And let's do phi equals pi upon 4 to pi upon 2. And let's assume that this function here, including these two guys, ended up being that guy, that guy. Let's say it was a costia. So basically, this fellow is going to get integrated along these three particular ones. So that's going to give me a 0 to pi upon 4 of a cosine function. The middle one's going to give me a 0 to 1 rho squared. Last one's going to give me a pi upon 4 to pi upon 2 of a sine function. So if I give you an integral already set up in its polar format, and you're lucky enough as we are here, it can be separated out. This guy here is going to get me a negative, not a negative, a positive sine theta. And this one here is going to get me that guy. And this one here is going to get me a negative. Okay, I'm just going to go dot, dot, dot now. Can you imagine that's equal to something like root 2? That'll be a third. And this guy will be whatever it is. And you put the pieces together and you're finished. So what we'll be doing next week is